things what our image is, and really those, thoughts about it. The theories are all over the map. The great majority of these theories are difficult to test in laboratory experiments, with the exception of one subclass that we can test with super neutrons. And so that's what So I think probably by now many people have seen this plot of the energy budget of the universe, the theoretical speculations for what the dark energy is, and all of that. It's still unclear what it is in a sense. What we can do is say a few things about it. Of course, probably most people in the audience will know the ancient quote about what you believe or not believe about cosmology. The land about cosmologists often err in doubt. It's a very well-known quotation. We had a colloquium in Indiana from Michael Turner, who told us that it's time to retire this quote, because cosmology is what he calls a precision measurement subject. And so I just want to show you a few examples of that. So as we know, most of our universe is in the form of energy, dark matter, dark energy, and we still don't know what 95% of the universe is. The cosmological parameters now come with error bars that are actually small. So this is a list of some of the cosmological parameters, just to remind you that the omega zero is the ratio of the determined energy density of the universe to the so-called critical density of general relativity. And that's, if you believe these numbers down to percent. These are the different numbers that come from cosmological analysis for the dark energy, the dark matter, and the contribution of everything else. Hubble constants known as sort of 2% level. It seems the age of the universe is known to reasonable precision. It's in new parameters, the number of light triple species of Big Bang closeness. This is where a lot of tests of cosmology come from. So these are all impressive numbers. And as you may know, a lot of that information comes from the precision measurements of cosmic microwave background radiation. So this is the usual picture you see of the temperature fluctuations. And if you take the angular power spectrum, plot it as a function of multiple moments, you get very well known pictures of relative intensity of fluctuations weighted by L plus 1 as a function of L, and extending out to L's 3000. That line that fits all this data is a theory. These are pretty pattern fluctuations. And it's where this is a piece of data that determines a lot of those parameters. And of course, the most shocking thing that probably happened in the last decade or so is this discovery of the accelerated expansion of the universe. This, of course, goes exactly the direction you wouldn't have expected. You would have expected, loosely speaking, that of a clump, and to slow down the expansion of the universe, but it goes the other direction. And by now, the later verifications of this initial measurement are certified by Sweden. This was the Nobel Prize a couple years ago, I guess, for discovery of dark energy. So, Michael Turner would say, this is a big deal. What is this stuff? What could be causing dark energy? There are some ideas. Just very quickly look at a couple of them. But of course, the attitude we should take is to try to search for it. And I'm not sure if everybody knows about the U.S. politics. For those who do. The attitude is clear. We got to look for this stuff. So, what could it be? The most conservative assumption is the term that Einstein famously threw away, the so-called cosmological constant. In other words, that something is an allowed extension of general relativity, and as Peter pointed out, that term gets a contribution from vacuum fluctuations of the fields of the particles we know well. And so we sort of can calculate that principle from our theories of nuclear particle physics. There's a problem, though, when the calculation's done, as you may know. If you add up the zero-point energy density of all the fields that we think we know, and do the integral, of course, it converges. But even if you cut it off in the most conservative way, you will get a number for the vacuum energy density, which is orders and orders of magnitude greater than the number that comes from the cosmological measurements. And I don't know if it's maybe 10 to the 70, 10 to the 50, 10 to the 100, depending on which fields you take. I guess the most dramatic way to say it is that it's the largest non-infinite discrepancy between theory and experimental physics. Also, just a quick reminder of what this business of vacuum energy does. You can do a very simple, almost thermodynamic analysis of it. Just take the first law of thermodynamics, and if I assume the vacuum, this dark energy is the ground state of some quantum field, then that ground state has no entropy, so I don't have a TES term here. And if I simply put in this energy is the vacuum energy density dE, then I can see that there's a relationship between the vacuum energy density and the pressure. And there's a negative sign here. And if you look at Peter's equations for the energy Wim tensor of fluids in general relativity, loosely speaking, pressure gravitates. So this P equals minus rho relationship between pressure and energy density leads to a number inside that equation. So you get an expansion of that. So that's one solution to dark energy, to say it's Einstein's term. But we have this 10 to the 80 discrepancy between theory and experiment, so maybe that's wrong. So what else could it be? If you want to construct a model for the dark energy, you have to add some degree of freedom. If you're not going to have it be the vacuum energy density. And so people have thought about how to add such a degree of freedom. There are a lot of constraints. Actually, Peter's talk maybe has a wax on them, potentially, depending on how those measurements go. But if you try to mess with gravity, as you know, there are many precision tests at many different scales. And then there are people who have tried to come up with ideas to modify gravity. The common theme of these ideas is they need some kind of screening of the effects that doesn't show up in a lot of precision tests, but still the entity reaches in space can exist and cause the accelerated expansion. So if you take, so the universal assumption of the theorists is always to imagine a scalar field, because a scalar field can have quantum numbers of vacuums. This has no spin. So you imagine having u degree of freedom as a scalar field, couple it somehow to the energy density, and then if you write the equations for fluctuations of this field in the presence of this matter, you'll get an equation that's got sort of the speed of sound for the fluctuations. If the field has a finite mass, you get the m squared term that comes from the Klein-Gordon equation. And then on the right-hand side, you've got a source term, which assumes some sort of coupling. Sorry, delta rho is the edge of the paper. So in general, this is a nonlinear equation. So what people have done in these so-called chameleon theories, and that's what I'll talk about now, is they try to construct a nonlinear coupling of this field in such a way that the field has an effective mass which gets very small and therefore can create dark energy if you're in vacuum. But if you're in a high density situation, that the range of this interaction becomes very short and therefore evades all the tests. So that's the dirty trick, and that's why it's called a chameleon. It hides in matter. And so it's just an equation. So people have constructed such actions to try to make an action for matter which will have this property. And there are ways to construct such an action. And as I said, you end up getting a situation where you've got an effective mass and therefore an effective range of this scalar field, which depends on the course of secondary potentials usually, and then this nonlinear term. So to figure out how this scalar field depends in a particular situation, you have to actually solve differential equations to see how it depends on distance. But generally speaking, it will be very short range when the density is high and very long range in vacuum. And so there's various kinds of nonlinear potentials you can put in to try to make this happen. And there's some constraints already in the parameters so that you don't violate various precision tests of gravity that already exist. So what does all this have to do with neutron interferometry? So let me say a little bit about what interferometry is. If you had a gradual quantum mechanics test by a guy named Sakurai, some part of Sakurai, he shows the picture of the experimental evidence for gravitational phase shifts of neutrons in the gravitational field. And that experiment was done by devices like this. So what these interferometers are is they're perfect silicon crystals. And what you do is you sculpt away pieces of the crystal to leave perfect crystals whose lattice planes are aligned perfectly. And therefore, what you can do is use those lattice planes as coherent beam splitters and recombiners for neutrons. So a neutron can come in and meet the diffraction condition in one lattice plane here. So part of the beam will go straight, part will be diffracted. And if the lattice planes line up properly, then you can still meet the coherent beam splitting condition here as well. And so you can coherently split the recombined beam and make neutron interferometry. So that's what these devices are. And this is just a picture of the facility in this. What's not shown, of course, is the nuclear reactor that's over here that makes the neutrons. The facility is actually a fascinating vibration isolation engineering object. So this facility has a 20-ton hunk of concrete which sits on air pads and is levitated. And then on top of that 20-ton hunk of concrete, there's a 1-ton granite table, which is also on air springs. And inside a thermally acoustically shielded room, there sits the small crystal that fits in your hand. So this object is very well vibration isolated. It has to be because the neutrons are coming in slow. And if the crystal moves by more than a fraction of the lattice position during the motion of the neutron, you lose the interference. But if you can meet that condition, then the interferometer works in the usual way of coherently splitting the beam and binding the beam. So, for example, if you put a piece of matter in one of the arms of the interferometer, that matter will make a phase shift of the forward neutron wave going through it. And that phase shift can be measured with this crystal. So that's the main application of this device, is to measure such precision conditions. We have used this device actually in the past to do nuclear fuel physics. And the point is simply that if you put gas samples like hydrogen, deuterium, helium in this interferometer, you can measure with very high precision, and by high precision I mean 3 digits, the coherent scattering length, and therefore the isolated field scattering length, to which nuclear fuel can try to use to constrain the force. So that's one application we made with this device. It's associated with nuclear physics. And this is just maybe a clearer picture of how this experiment works. This is a top view of the beam diffracting from the blade of the perfect crystal, taking its 2 paths. And for the experiments I just mentioned, we had a vacuum chamber which one area was evacuated and the other was filled with the gas of interest. This is an actual picture of the device where we see the perfect crystal. The 2 neutron detectors detect the 2 places where interfering beams go. It's in the beam. And that's a picture of the sample cell we used for seconds. So what we want to do is exploit the fact that if this dark energy exists, it will couple to the neutron. The neutron is too small to kill the Canadian field. And so if I have a vacuum chamber with a bunch of walls, the walls are a source of the Canadian field in principle. If that chamber is evacuated to a very low pressure, the Canadian field will blow out and occupy the space. But if I fill it with gas, the Canadian field will collapse and only extend a very small distance away from the walls. So our idea is to search for these chameleons by doing an experiment like that. So we intend to construct a device in which we put this perfect crystal neutron interferometer, the entire thing, in a vacuum. So I've got an interferometer in a vacuum. On one of the paths of this beam, we'll put a source of high density like lead, like a lead tube around one of the beam arms. So that lead will be the source of the helium field that's closest to the beam. And then, if there were this dark energy contribution affecting the neutron, the beam that goes close to the lead will couple to that field and make a phase shift. And then, if we fill this vacuum chamber with gas, that will kill the chameleon field, but give the same phase shift for the 2 parts of the beam. So if I take the difference between those 2 measurements, I should this is actually a calculation of the phase shift that the chameleon field would give to a slow neutron in this experiment as a function of the pressure of the gas. And what they did was they solved the nonlinear equation, which determines the spatial distribution of that field. And these are for different assumptions of the nonlinear potential that's needed to generate the chameleon at different ends. So there is, of course, some model dependence in prediction. One, though, is that by changing pressure, we have a specific prediction for how that phase shift will change. And it turns out, according to the dark matter theorists who speak with us, that this technique is one of the most sensitive ways to search for these chameleon fields. So this is a plot of existing constraints. These are laboratory constraints on this idea. The regime here is excluded by the well-known precision gravity experiments at the University of Washington, where they have these torsion balances and very carefully measure gravitational interaction. And then in this other stronger nonlinear coupling regime, this is the bound that is projected by our experiment from the 20Interferometry. And as it turns out, this chameleon idea has, of course, been extended by the theorists to couplings to photons as opposed to, in addition to matter couplings. And this is a recent plot of various pieces of parameter space that have been excluded by experiments so far. Things that are colored, so collider data, torsion, pendula, precision gravity measurements, and slow neutron measurements. And this experiment, this is existing or soon to be taking data, and then these other lines are extensions based on other types of measurements. So the 20Interferometry measurement we do a little bit better is pushing this direction. The point, I guess, of this plot is that you can imagine the possibility that this is a theory we can kill. And so we made a proposal to this 20Interferometry facility to conduct this measurement, and we're prepared. So I think that's time to conclude. So what I'd like to conclude is that dark energy is a great history with its origins. The most conservative assumption theoretical calculation gives us something that's wildly different from what we observe. So maybe we should have some theories which are not simply the vacuum energy density, come from that direction. The great majority of the theories, unfortunately, are difficult to test in the laboratory, with the exception of this idea of a nonlinear scalar field coupled to local matter density. And it turns out that slow neutrons are a very sensitive way to search for the possibility of such a field. And I guess the attitude I would take towards this work is that I think dark energy is so interesting that if you can kill an interesting idea with a laboratory experiment, you should probably try to do it.
Are there any questions?
Yeah.
So, Mike, is the fact, is it because of the nonlinear coupling of the mass density that the neutron is too small to hide the chameleon? Dark energy? I mean, why is it too small?
It's too small because there's a length scale involved in the theory. So if you take the dark energy density and do do dimensional analysis and convert it into a distance scale. That distance scale is approximately 100 microns. So since the neutron is, and that dimension is implicitly in the parameters of the theory. And so the neutron is so much smaller than that smallest length scale of field that's the reason it doesn't matter. So it's an advantage of being small.
If not, we take a